Okay, so let's get started. So first announcement, the midterm was marked and so was assignment 2. So the marks you can find online by logging into Moodle, and you can always go there to monitor all your marks. Generally, I think people did okay on the midterm, and hopefully the review session before it was helpful. So if there's no questions about the midterm or assignment 2, I'll proceed with the summary of last time. Okay. So last time we looked at the properties of the Lagrangian. And today we will continue with that. So a few of the properties that we looked at last time, we saw that it was invariant under point transformations. These are coordinate transformations that take you from one set of coordinates to another set of coordinates, and those transformations may depend on time but not velocities of the coordinates. And so of course this is a useful property because it allows us to choose which set of generalized coordinates we want to use to describe a problem, for example Cartesian or polar. And so it's good that the Lagrangian description of mechanics be invariant under these point transformations. We also saw that if you have two different systems given by two different Lagrangians, let's call them LA and LB, then the Lagrangian describing the total system is given simply by the addition of the two Lagrangians. We also saw that the equations of motion are unaffected if you multiply the Lagrangian by some constant. The equations of motion are unaffected. And we saw that that was akin to changing the definition of mass. And we also saw that L, if you add a total time derivative to it, the equations of motion are also unchanged. Because the equations of motion are given by Hamilton's principle, which says that the integral of the Lagrangian over time must be stationary, and if you add a constant time derivative or time derivative to the Lagrangian, that integrates out when you take the action. And as we saw last time, that didn't change the equations of motion. Okay. Any questions about that? And the last thing that we saw was that the Jacobi integral which is given by the sum over the degrees of freedom of qi dot multiplied with di L by di qi dot minus L was equal to a constant if L not depend explicitly on time. So it's di L by dt equals 0. And we found that, well, this equation is one that we used back in variational calculus. And then we also saw last time that often H is T plus V, which is equal to the total energy. And so again, we saw that if the Lagrangian does not depend explicitly on time, then it appears that the total energy is conserved. And then we did an example of that for a simple harmonic oscillator. Okay, so today we're going to look at what's called cyclic coordinates. This is a very important theme in Lagrangian mechanics. Cyclic coordinates are ones that don't appear in the Lagrangian. So we say that Qi is cyclic if the partial derivative of L with respect to Qi is equal to 0. So the velocity, Qi dot, may appear in the Lagrangian, but if the coordinate itself doesn't appear in the Lagrangian, then we say that that coordinate is cyclic. Okay. So consider the Euler-Lagrange equation, which tells us that d by dt of di L by di Qi dot minus di L by di Qi equals 0 for all Qi, for all I. If di L by di Qi is equal to 0, the second term, right, then we have d by dt of di L by di Qi dot equal to 0. And of course, when the time derivative of something is equal to 0, that means that something doesn't change with time. So that means that if I define a new quantity which I'll call Pi to be di L by di Qi dot, that quantity there is equal to a constant. And we'll see in a few minutes that we call this the generalized momentum. Okay, so let's do an example of that. In the notes, this is example 4-8. Particle in a gravitational field. So we know that the Lagrangian is the kinetic energy as mx dot squared plus y dot squared z dot squared minus the potential energy minus mgz. Okay? So if you look at this Lagrangian, you ask yourself, which coordinates are cyclic? These are coordinates that don't appear explicitly in the Lagrangian. So x and y are cyclic. Z, on the other hand, is not, since it appears in the potential energy. So we have diL by dix is the same as diL by dy. It's equal to 0. So both those coordinates are cyclic. So what are we told for a cyclic coordinate? We're told that if you take diL by that coordinate dot, you get a constant. So let's consider px, which we define as diL by dx dot. All right. So diL by dx dot is going to be a constant. So let's take that derivative. So x dot, there's a half m x dot squared. So diL by dx dot is mx dot. And that's got to be equal to a constant. Of course, that looks awfully familiar. Similarly, py, which is diL by dy dot, that's my dot. And that's going to be equal to a separate constant. So Z, on the other hand, is not cyclic, and so there is no diL by dz dot is not conserved. So you can still define Pz to be diL by dz dot, which will be mz dot, that is not equal to a constant. This makes sense, right? It's a particle in a gravitational field, so gravity acts only in the z direction, so there are no forces in the x and y direction, and so the momentum in the x and y direction is conserved. And so presumably the initial conditions would allow you to calculate what that momentum is. All right, so the equations of motion are very simple, right? For the cyclic coordinates, the equation of motion is that dx by dt is equal to px over m. And similarly for y, dy by dt is py over m. The initial conditions can give you px and py. All right. So then, of course, x can be integrated immediately, and so can y. So let me write them at the bottom. X of t would be equal to px over m times t plus some constant. And same with y of t. Okay, so let's note something else. That our Lagrangian didn't explicitly depend on time. So that means the Jacobi integral, h, which was equal to sum over I diL by diq I dot times qi dot minus L must equal a constant. So let's calculate that term. So the sum over I goes from x, y, and z. So the diL by x dot we already found to be mx dot, right? Times x dot, so we have mx dot squared, plus my dot squared, plus mz dot squared. Now minus the Lagrangian, so minus a half x, oops, sorry, there's an m in there, minus a half time m times x dot squared plus y dot squared z dot squared plus mgz. Right, this part here is all L. And what we're left with is a half m times x dot squared plus y dot squared z dot squared plus mgz, which you can recognize as the kinetic energy T plus the potential energy V, or in other words, the total energy. And so the equations of motion, I already showed you how you can get the equation of motion for x and y, right? And so you can, if you want the equation of motion for z, you can apply the Euler-Lagrange equation, as we have in the past. Or you can also use this other method that we found last time in this particular case, where you can use the conservation of energy. All right, so you have the total energy, which you can calculate, right? E, based on the initial conditions, is a half mx dot squared plus y dot squared plus z dot squared plus mgz. So you can isolate z dot to get the equation of motion, first order differential equation for z. So if I do that, I think you get z dot is equal to the square root of 2e over m minus 2gz. I'm just going to have to write it out. That's minus minus 2gz minus x dot squared minus y dot squared. And so, of course, x dot squared and y dot squareds are constants. Okay? So here we end up with a first order differential equation for z. It's fairly straightforward to solve. And trivial first order differential equations for x and y. So you could have solved this with the Euler-Lagrange equation, but it's much more simple when there's cyclic coordinates to get rid of them. All right. Any questions about that? So next, let's introduce formally the generalized momentum. So with each coordinate, we have associated with it what we call the generalized momentum. Sometimes we call it the conjugate momentum. So Pi is defined to be dial by diqi dot. And that's what we call a generalized momentum. And it's also the conjugate momentum to Qi. So it doesn't necessarily have units of momentum, just like generalized force didn't have necessarily units of force. So again, let's look at an example. In the notes, this is example 4-9. Consider the Lagrangian of a free particle in polar coordinates. So the Lagrangian for a free particle in polar coordinates, since it's a free particle, it's only t. And so the kinetic energy in polar coordinates is r dot squared plus r squared theta dot squared plus z dot squared. So if we calculate, so we have 3 degrees of freedom, so we have 3 generalized momenta, and those momenta are PR, which is diL by dir dot, and diL by dir dot is mr dot. We have P theta, which is diL by di theta dot, and that's equal to mr squared theta dot. And then finally we have Pz, which is diL by di z dot, and that's mz dot. So let's look at our Lagrangian and see if there are any cyclic coordinates. So theta and z are cyclic, but r is not cyclic because r appears in the r squared theta dot term, right? So we have theta and z that are cyclic. So that means p theta and pz are constants. So what is p theta? So first, so what is p theta for a single particle? It's mr squared theta dot, and so that's actually angular momentum about the z-axis, right? And pz obviously is the linear momentum. In z. And the momentum in r is obviously not conserved, right? Because if the particle is a free particle, it's going to go in a straight line, and there's no straight line where r is constant. So this, trivial example highlights 2 things. One is that the choice of coordinates might give different numbers of conserved quantities. If we had chosen Cartesian coordinates to describe our free particle, then we would have found that all 3 of the momenta were conserved, right? Because the Lagrangian for a free particle in Cartesian coordinates is just a half m x dot squared plus y dot squared plus z dot squared. And so all the coordinates are cyclic, and all the momenta are conserved. In this case, we chose a different type of coordinates, namely polar, And then we found that one of the conserved quantities has a different dimension than the others, p theta, and that's actually angular momentum. So we just found that angular momentum is conserved. Well, that's a good thing. We expect it to be conserved. Any questions about that? The next topic becomes a little bit more mathematical. So the question is, we found that we have these cyclic coordinates and that their equations of motion can be written trivially. So maybe there's a way to just ignore them and reduce this to a smaller problem with less degrees of freedom. And so indeed there is a way to do that Ruth came up with using the Roothian. So let's look at the Roothian and eliminating cyclic coordinates. So let's say that we have n degrees of freedom and we've labeled our coordinates such that the first k coordinates are cyclic. Okay? So if that's the case, then di L by di Q I dot, we're going to set this equal to a constant, which we'll label beta. And that's true for I equals 1 to k. So these betas are constants. All right, so we've labeled the coordinates so that the first k are cyclic, and then we know that di L by di generalized velocity of that coordinate is equal to a constant. And we'll call it beta I to identify it as constant as opposed to pi, which we'll assume are not constants. So our procedure is to first write L using the beta i's. So we can always write the generalized velocity in terms of the momentum, right? It's usually either m times the velocity is equal to the momentum or something more complicated like the angular momentum that we had. But you can replace all of the velocities, the constant ones, with the beta i's, right? And then we introduce the Roothian R as the Lagrangian minus the sum from I equals 1 to k, so the sum over only the cyclic coordinates beta I times qi dot. And so this Roothian is a function of the qi's the qi dots, the beta i's, and t. So the QIs, there's n minus k of them. And then there's k of these beta i's. And the qi dots that are here, similarly, there are n minus k of them. So consider now the variation of R. So R is a function that depends on the qi dots, the beta i's, and t. All right, so if we take the variation, we have to take, using the chain rule, the variation over all the different variables. So we have the sum of I equals k plus 1 to n of di r by di qi delta qi. All right. R depends on the QIs, but the only ones that appear are the ones from k plus 1 to n. Similarly, plus the sum from I equals k plus 1 to n of di r by di qi dot, delta qi dot, plus the sum of I equals 1 to k of di r by di beta I delta beta I, and then plus di r by di t. Okay? So that's just simply writing out the variation for a general function that depends on these various coordinates. Now this has also have to equal to delta of the definition that we use for R. The definition that we used for R was that the Ruthian is defined by L minus the sum from I equals 1 to k of beta I qi dot. All right, so that's, those two have got to equal each other. So now L depends on the qi, the qi dots, and t. And we've written L so that we've eliminated all the velocities, and the cyclic coordinates weren't there from I equals 1 to k. So if we take this variation, first I have the variation of L. So that's the same procedure. So the variation of L is going to be the sum from I equals k plus 1 to n of di L by di qi delta qi plus the sum from I equals k plus 1 to n of di L by di qi dot delta qi dot plus di L by di t, and then minus the variation of the second term. So that's minus delta of the sum of I equals 1 to k of beta I qi dot. I'm going to write that in the next page here. So rewriting the first part, which is just the variation of the L's. So that's the sum of I equals k plus 1 to n of di L by di qi delta qi plus the sum I equals k plus 1 to n of di L by di qi dot delta qi dot plus di L by di t, and then minus the sum I equals 1 to k. And now it's the variation of beta I qi dot, so that when you take that variation, it acts just like doing the product rule. So you end up with beta I delta qi dot plus qi dot delta beta I. Okay? So writing this all out, oops. So the first terms are all the same. I guess I'll write them down again. Sum of I equals k plus 1 to n of di L by di qi delta qi plus the sum of I equals 1, I equals k plus 1 to n of di L by di qi dot delta qi plus di L by di t minus the sum of I equals 1 to k. Now the beta I I'm going to write as di L by di qi dot. So that's times delta qi dot. Plus, minus the last term. Sum of I equals 1 to k of qi dot delta beta I. Okay, so now this last term here, the second last term, I'm sorry, is equal to 0. Because we rewrote the Lagrangian L by eliminating the qi dots that are from 1 to k. So at one point I made a sentence saying that we can now remove the velocities that correspond to the cyclic coordinates, and I can replace them by the constant beta i's. And so then L doesn't depend on the first k qi dots. And so that term is equal to 0. So we compare this, to the other form of the delta R that we wrote. So earlier, we just wrote that delta R was equal to the sum of I equals k plus 1 to n of di r by di qi delta qi plus the sum of I equals k plus 1 to n of di r by di qi dot delta qi dot plus the sum I equals 1 to k of di r by di beta I delta beta I plus di r by di t. Right. So these two must be equal to each other. So if these two expressions for the same thing are equal to each other, then I can look at all the terms that have delta qi's and group them together, and they have to be equal. So let's look, for example, at, in the top expression, I have the first term here with the delta qi, and in the bottom expression, I also have a term with the delta qi. So that means, so the sum over the same indices, right, from I equals k plus 1 to n, so that means that di L by di qi has to be equal to di r by di qi. That's by matching the term that's in front of the delta qi. And so if I do that for the other terms, what I find is that di L by di qi dot is going to be equal to di r by di qi dot. Qi dot is equal to minus di r by di qi, by di beta I, I'm sorry. So that, for example, I'll underline that term in red. That's by matching these two guys. So the coefficients of the delta beta I in the above expression is qi dot, and in the bottom expression it's di r by di beta I. And then finally we find that di L by di t is equal to di r by di t. So let's make sure we know what the indices are. So in the first two equations, the I goes from k plus 1 to n. In the second equation, I goes, and so in the third equation, I goes from 1 to k. So in particular, note that di L by di qi is the same as di r by di qi, and di L by di qi dot is the same as di r by di qi dot. So that means that R will also satisfy the Euler-Lagrange equations. Because L does. So we can write that d by dt of di r by di qi dot minus di r by di qi is equal to 0 for I equals k plus 1 to n. And that's exactly what we set out to do. We asked ourselves, isn't there a way to solve a problem by completely getting rid of the k cyclic coordinates? And the answer is yes. You have to construct this quantity called R, the Ruthian, and then you get the k plus 1 to n differential equations. So that gives you the equations of motion for the I equals k plus 1 to n, and the equations of motion for the I equals 1 to k are trivial. And those are just that qi dot equals minus di r by di beta I. That's for I equals 1 to k. So we've separated out the problem formally into a simple set of k differential equations for the cyclic coordinates and the traditional Euler-Lagrange equation, which would typically be second order for the non-cyclic coordinates. So let's summarize the procedure. So if we want to solve a problem using the Ruthian, the first step is to write the Lagrangian and identify cyclic coordinates. And the second step is to calculate the beta I. And use them to eliminate the corresponding qi dots from the Lagrangian. 3, you write the Ruthian. So that's R is equal to L minus the sum I equals 1 to k of beta I qi dot. And then 4, for the cyclic coordinates, you have qi dot is equal to minus di r by di beta I. And then 5, you have the Euler-Lagrange equations for the non-cyclic coordinates. But instead of L, you use R. So let's do an example. It's 410 in the notes. And let's use the Ruthian for a particle in a gravitational field. So first step is to write out the Lagrangian. And so we just did that earlier today. So that's the kinetic energy, half mx dot squared plus y dot squared plus z dot squared minus mgz. Okay? So we've already identified that x and y are cyclic, So that means that di L by di x dot, which we'll call beta x, is equal to a constant. That's also equal to mx dot. Similarly, di L by di y dot, which is equal to my dot. That's going to be equal to a second constant, which we'll call beta y. So now we have to rewrite the Lagrangian L, but we have to eliminate the x dot and the y dot, right? So we want to eliminate x dot and y dot from the Lagrangian in favor of beta x and beta y. So we have x dot is going to be beta x over m, and y dot is beta y over m. Right? So the Lagrangian with those replacements, L is equal to a half m. Then we have beta x squared over m squared plus beta y squared over m squared plus z dot squared minus mgz. So now the Ruthian, it's given by L minus the sum from I equals 1 to k of beta I qi dot. Alright? So if I sub that in on the next page, and get R, so it's equal to L. So that's a half m beta x squared over m squared plus beta y squared over m squared plus z dot squared minus mgz, that part is L. And then minus beta x dot minus beta y dot. So now, again, I'm going to remove the x dots and y dots in favor of the beta x's. So if I rewrite this, the first term is unchanged, so I have a half m beta x squared over m squared plus beta y squared over m squared plus z dot squared minus mgz minus, so beta x times beta x over m. So that's beta x squared over m minus beta y squared over m. So collecting all the terms together, I have a half m z dot squared minus mgz. Then I have minus beta x squared over 2m and minus beta y squared over 2m. Because I have a half beta x squared from the kinetic energy minus a whole beta x squared. So I'm left with minus a half of each. Okay. So now we have the Ruthian. So the Ruthian depends on these constant terms, beta x squared and beta y squared. And then it depends only on the non-cyclic coordinate. So it's got the non-cyclic, the velocity that goes with the non-cyclic coordinate z dot, and it has the cyclic coordinate z dot in it. So if we go back to our prescription, to get the equations of motion, right, we have for the non-cyclic coordinates, we use the Euler-Lagrange equation, and for the cyclic coordinates, we write out this trivial equation. Okay? So for the cyclic coordinate, thus the equations of motion so for the cyclic coordinates, we have x dot, which is equal to minus di r by di beta x. And so that's going to give us beta x over m. And so that's trivial. X of t will then be given by beta x over m times t plus some constant. And do the same with y. Y dot will then be minus di r by di beta y. So minus di r by di beta y is beta y over m. And that integrates trivially to y of t equals y naught plus beta y over m times t, as we had before. And then for z, we have to use the Euler-Lagrange equation. So if I do the Euler-Lagrange equation, I have d by dt of di L by di z dot, which is mz dot, minus di L by di z, so that's plus mgz. And so there, and I'll get a second order equation of motion for z, namely that z double dot. Oops, there's no z there. Once you take the derivative, z double dot equals minus g, as you would expect. There's a small mistake in the notes there. There shouldn't be a z. Okay, so that's actually all I had planned for today. We went over it a little bit faster than I thought we would. So on Wednesday, we'll start with conservation laws, and then after that we will skip the next chapter, which is applications of the Lagrangian, and we'll go straight into the Hamiltonian, and we'll come back to the applications if we have time at the end of the course. But it's much more important that we start looking at the Hamiltonian, since it has a connection to quantum mechanics. Okay, any questions about this material? Okay, if there's no questions, then we'll meet again on Wednesday, and we'll start with looking at conservation laws. Thank you, everyone.